start slowly, and the others can also join. Okay,
Okay,
so that
Banu.
we are noted. Okay, so what we discussed last night was k-means clustering, right? So k-means we need to understand is that the user becomes the supplier of k, and because of some experience he knows what that k is, right? And once that k is provided, the algorithm starts partitioning the data, right? So you had seen, like example, if you say k equal to three random centers are selected, and then distances are calculated and they are grouped according to whichever is the nearest thing, right? And then it proceeds and stops at a particular point, right? So when we find a very minimum number of points changing their position, so that means after every iteration the points do change their membership, right? So they may be belonging to cluster number one, then they may go to cluster number two, and so on and so forth, right? So when you see that this membership stops, right, this membership stops changing, then you say, okay, this is the final result, so stop and print the result, right? And that is the final cluster membership. Okay, now if you look, there are limitations of k-means. Of course, every algorithm has a limitation, and that is the reason that we get newer algorithms, right? So limitations give rise to newer algorithms. So k-means generally will give rise to unequal clusters. That is one thing. The clusters are not of equal size. There is a heavy disparity in terms of the size of the cluster. One cluster may be small, the other may be very big. That is there. Then there is non-globular shapes. Ideally, what we want is that our cluster should be spherical in nature. So, sorry. So that means what we want is our cluster should be as far as possible like a round ball, right? A spherical ball. But then what happens is, because of this clustering things, the shape of the clusters can be elongated, right? It can be like this, like American football and all this. So if you have elongated things, then what happens? This cluster becomes bit, let's say, difficult to define. This is one. And the second thing is the chances of overlap become very high, right? So elongated clusters is one more issue that is faced when you are like looking at these clusters. Just give me a moment, please. So this also becomes a issue, isn't it? So the shape becomes very important, isn't it? Because what can happen is, the if it is elongated in one direction, then the chances are, if there is another cluster, overlapping can happen, right? This can overlap. This cluster has entered the territory of the second one. So these points are then, so this area, this cluster also has a membership, and this cluster also a membership. But always remember, the membership is unique, right? A point here doesn't mean that it belongs to both the cluster. That will not happen. What will happen is they still will have unique membership. The guy here will, let's say that I belong to this cluster. The object here will be telling that this belongs to this cluster. They'll have the unique memberships, but somehow these areas get overlapped, right? So a funny thing, though the area is common, but they'll be claiming we have different kind of memberships, right? So that is what happens here. So that needs to be kept in mind. Uh, so we go to hierarchical clustering, which solves some of these problems. I'll not say it solves everything, but solves some of these problems. And also hierarchical clustering is to be used when we do not know how many clusters actually to have, right? Also remember that we generally, a better idea is never go for a pure, never go for one of the approaches. That means what approach should be taken? We should not be taking one of the pure approaches. That means don't say that I'll only do hierarchy clustering or I'll only use k-means. That should never be done. A better approach is, if you don't have an idea, or even if you have an idea, start with hierarchical clustering, use the dendrogram, come to a tentative solution, the most possible solution, and then use k-means and simulate 2 steps ahead and 2 steps backward kind of a solution. So what I'm trying to say is, take the data, look at the dendrogram, and find out a tentative solution. So the tentative solution will say, okay, this particular data set has 6 clusters, for example. take this as a tentative solution, not the final solution. Okay, and then come back and you start using k-means. So simulate 6 clusters, 7 cluster, 8 cluster, 9 cluster, and similarly simulate 5 clusters, 4 clusters. So simulate cluster solution over a range 4 to 9, and then compare which one is the best, right? And then go for that. So iterative, the process should be iterative. Also, a good thing is that in R at least there are packages available which can help you decide the number without using this. Dendrogram is one of the method. Don't take it as if dendrogram is the final God-given thing. Okay, so there are other methods which are available. There are around 30 metrics available if you want to decide on the number of cluster. What R has done is there is a package by the name of NBClust. And these 30 matrices are all packed into that, right? So you can use NBClust. NBClust will give you an idea on how many number of clusters should be there in a solution, right? So you can take advice from NBClust. You can look at the dendrogram. There are many ways. So today we'll run the codes and you'll see there are different ways of doing these kind of things, okay? But hierarchical clustering, we know it's agglomerative devices. I'll not, what are the strengths? By cutting the dendrogram at the proper level that I told you yesterday. Okay, agglomerated devices, the story I've told you, I'll not repeat it again. So this is the proximity matrix or the distance matrix. I told you how it happens. So if these two combine, P1, P2 combine, then you designate it by cluster 1. So instead of these points which were large, you start getting clusters. Your cluster dimensions start reducing. It starts from n by n, and the cluster dimension will become 1 by 1, right? As the cluster proceeds, there will only be one cluster. So it's going to become 1 by 1, right? So this is what is going to happen, right? So this is known as the merging scheme, and that's what the dendrogram shows you, okay? Now, to the final thing, and then we'll start our codes, right? Just one simple question to ponder. Let's say these are 2 points, right? This is point 1, this is point 2. How do you find the distance between them? So these are the 2 points A and B. I can use any matrix. I can use Euclidean between them, assuming this is a ratio data, right? If I'm saying points, then it can be anything, right? This can be actually a ratio data, a real value, let's say space. This can be a real value space represented like this, a real number space, okay, which has dimension n, can be like this, or this can be this may not be a real value scale where we have categorical data, right? So if it is a categorical data, it's not a real value space, but it's a space which you can represent as with some dimensions, okay? So how do you find the distance between these 2 points? So if you want to find out the distance between these 2 points, then you can use Euclidean, you can use probably whatever Mahalanobis or block distance or any, there's so many distances that you can use, or a Watt's d square, anything you can use. Let's say I want to find, this is situation number 1, which is simple. We have answered it simply. Now let's say this is another situation where we have multiple points and I want to find the distance from a single point, right? This is situation number 2. So what is the distance between this group and this single point, isn't it? And this is what is required. Intermediate stage is what? That this is some intermediate cluster and there are points available. So if this point is near to this cluster, then this will become a part of this. And if it is not, it will not become a part. So how do we define a distance between this group and this, right? So let's have a third situation. So this could be like this. This is a group out here. Okay, bunch of points. And there is a group here. Let's say this is a smaller group, let's say. Okay, again, some bunch of points. Right. So how do we define a distance in this case? How do we define a distance in this case? And how do we define a distance in this case? Right. That's the question. So generally what happens is there are few approaches, right? Example which are written here, which is shown here. The first approach is known as the min approach, right? Or you can also call it the nearest neighbor approach, right? This min approach is also known as the nearest neighbor approach. nearest neighbor approach. What is the nearest neighbor approach? The distance is, and it applies to this one and this, both these cases. So the distance between two is the distance between the nearest neighbors. So this is the point which is nearest. So I'll say the distance between these two is equal to this. Or if I look in this case, these are the nearest neighbors. So the distance between the clusters is equal to the nearest neighbor. So this is also known as linkages, right? So just remember, what is that? We call it linkages, Linkages, right? Linkages. This is also known as linkages. So we have to define our linkages. Right, so linkages. So the first kind of linkage can be what? So all of these are linkages. What are linkages? These methods of linking distance are known as linkages. Okay, so this is linkages. So this can be the minimum thing. The other approach is this maximum. Some people call it maximum, or you can call it the farthest neighbor, right? This is known as the farthest neighbor approach. So what is the farthest neighbor approach? The the 2 points which are the maximum distance become your actual distance. So let's say these are the 2 points which are farthest. So this is your intercluster distance. Or let's say these 2 points are the farthest. Let's say here, if I look at this, then let's say these 2 points are the farthest. So then this becomes your intercluster difference. So the intercluster distance is also known as linkage, right? So this is, and other names also. So when we go, we'll see, but this is known as linkage, right? Then the third approach is known as group average. So what is a group average? Let me show you like this. Let's say these are the things. So if this group has m points and this group has n points, then how many distances are possible? M into n. So I'll calculate all the m into n distances, right, and take an average of it. So m into n distances divided by this is, I'll take these distances of all m into n pairs and I'll take an average of that. That is m plus n, right? So this would be the average distance. So this average distance, this group average, this then can be defined, right? By default, if you look at the group average is your method, right? Is your linkage method by default if you don't give anything. This is by default, and I think this is better than others. You understand why? Because see here, what is happening is just one point is deciding the distance between the cluster, which can be very risky, isn't it? Which may not be the truth. So these two are just one point based solutions, and average is taking everything into account. So this being a true representative, this will be a true representative, right? The others, there are chances that this may go wrong, isn't it? This may absolutely go wrong. So that is the reason that we'll trust a group average more as compared to anything, because all the points are playing a role, isn't it? In the group average, every point is playing a role in deciding the distance. So that is why this is the default. This is better, but as I said that this is just like this can be a tentative answer. You can go ahead and decide things. And then the fourth approach is the distance between the centroids. So what you do is, and basically this is also 2-point based method. So you take a average of here, this thing, and you'll get a centroid. All of you know what a centroid is, right? And you'll have a centroid here. So calculate the centroid and calculate the distance between them. This is known as the centroid distance. There are 4 possible methods. Okay. So now very quickly coming to very quickly summarizing the clustering approach. What are we doing? So let's have the complete thing. Okay. So this is what is happening. Min max. I've shown you. This is the average thing. This is fine, right? So this is all. So now let's very quickly look at the steps and let's then jump on to the codes. So the first is that you supply a data matrix, right? So that is a data matrix. This data matrix is converted into a distance matrix. So you convert into a distance matrix, right? And then you have to, so here you need a selection. So this is your selection point, right? So you have to make a selection in terms of what? That what distance matrix, what distance measure. So I'll say distance measure are you going to use? So as a machine learning expert, this is your decision. What distance measure are you going to use, right? Then this Once you get this, then what will happen is this thing, then it will start the clustering process. It will result into the cluster. But here one more decision point comes, that what linkage are you going to use, right? So there is a decision on the linkage also. Generally let it be average, but this is a decision point. You can understand, you can alter it if you want. So you can say a linkage point, right? What linkage you want. Okay, so this is how it goes. Okay, then also if you look at clustering, you can make a flow diagram if you want. So if you want to do clustering, so the first question is, do you know the number of clusters, right? If you know this is the first decision point, right? No, this is not, wait a minute. So I want to start clustering. So the first decision point will come. What is that decision point? Do I know the number of clusters, right? So if I know the number of clusters, then yes, then I'll go for k-means. Then k-means is my answer. I'll go for k-means. If yes is your answer, then you go for k-means this side, right? So this would be your k-means or k-medioids, right? We'll discuss what a k-medioid is. The other side could be I don't know. Then what do we do? If you do not know it, then go for the hierarchical clustering, go for hierarchical clustering, right? And then back it up by k-means. Always understand. So if you don't know it, go by SC and then do k-means. You have to do k-means, right? And then do some iterations and come with a final solution. This would be a final solution. So use a combination approach. So this is the final solution here, right? So now let's open the codes before finishing off all the slides, which probably right now may not be a very useful approach. So let me open the codes for you. Just give me a moment. So we are ready. So this is the file. I opened it for you. So this is the clustering thing that we'll do, right? So here are the codes. So I mean, the number of codes are large, so we'll have to like hurry up in this case, okay? Because you can see we have to cover almost 367 lines of codes, right? So what I'll do is instead of starting at the top, I'll start at the bottom, right? Because this is a case study. So this will give you a good idea of the approach, right? So that's why I'm starting at the bottom of it, the car case study. So this we'll do first, and then we'll go up and then do that, right? So we'll have a different kind of approach. So let's start with this. And so this is a data set. Let me see if the data set is here. Yes, the data set is here. Let me copy this and put it into our folder. Right. So this, let me show you the data set. So it's a very simple data set. Why a simple data set? So that you can understand it. If you understand the data set. No. Okay, so if you look at this data set, it's a very simple kind of a data set. So the first column is about the country of make. You can look at this. So which country the car was made. So you can see all sorts of countries here: US, Japan, Germany, Sweden. Not a very large data set per se. Only 38 cars here, right? So that's all. So a small data set. And these are the models. I do not know any of these models, right? So Datsun 510, Dodge Omni, Audi 5000, all those. So these are all the names of the car models. Their country of make: Sweden, France, Germany, US, Japan, all of them. So European, Japanese, and US cars. Basically, you can put it this way, because Germany, Sweden, France, all of them are these European countries. Then this is miles per gallon, right? The Americans generally measure it by miles per gallon. And then it is weight, the weight of the car in tons, the drive ratio. I mean, if it is a racing kind of a thing, the drive ratio would be smaller, because you can't change from 1 to 2 to 3 to 4, 5. You can't have 4 gears in a driving racing car, right? The drive ratio needs to be shorter, so that quickly, I mean, it can be put in the top gear, right? So lesser the drive ratio. If you look at the drive ratios, you can understand this would be of a very speedy kind of a car, right? And the drive ratio is, I like the Japanese thing. If you see it, right, or if you look at this, then that means that this should be more of a city driving kind of a thing, right? Then only your drive ratios higher. Horsepowers are given, so you can see 155 horsepower, then the displacement of cc and cylinders, the number of cylinders which are there. So this is the data set, right? And we'll be using it for our clustering purpose, right? Displacement in cc, or you can say 3.5 liters divided by 100 will become your liters. So really, I mean, 3.5 liters of engine should be a big engine, isn't it? So, okay. So we'll read in this data set. I'll just set the working directory. And we are reading the data set directly from there. All right, so I'll clear this space. So I'm reading the data set, and we'll just ensure that this is what we wanted to read. So I did a head, and you can see 6 rows here. So that data set is used correctly. Now, when I go for, let's say, so we'll follow the steps that we discussed. So when I go for clustering, I'll remove the first two columns. While I'll remove the first two columns, there are different reasons why I'm removing these first two columns. One, I'm removing this first column, and I want to see if based on this data, will the clusters turn around to be country specific? That's what I want to test. So I have a hypothesis that the US cars, European cars, and the Japanese cars are different in nature. So I want to test this hypothesis. If I want to test this hypothesis in this case, then clustering is the method by which I can test this, right? So the country, anyway, I want to test, that's why I'm removing it. Now, the model also I'm removing, the car column, which is there, I want to remove it. There is a different reason why I want to remove that. Why I want to remove it? Because all the models, all the models, if you look at it, they are different. There are 38 different models, isn't it? So if you look from our perspective, what is going to happen is there would be 38 codes. So if all the data in a column happens to be unique, then what is going to happen? And if I try to cluster it, then what is going to happen is that there would be more number of columns which would be formed. So so it is very important that you look at that's why I say that doing a descriptive analysis of your columns is very, very important. So if you find that all the entries in a column are different, then this will give rise to either n number of solutions. That means the number of let's say clusters would be either n, which is there, or alternatively the number of clusters would be very high. So both the things are bad. So we need to remove any such column which has unique values, right? More unique values, where the unique values are very, very high, because it will distort. It may or it may not, but chances are that it may distort your cluster solution, right? So that for that reason, I need to remove this. So how do I remove it? It's a very simple thing. By now you would have understood. So I'm making a new data by the name of cars.use, just a name, you can give it some other name, and say cars in the square bracket, comma, minus C12. Minus means remove 1 and 2, right? So 1 and 2 would be gone, and MPG, weight, drive ratio, horsepower, displacement, cylinder is what would be left, right? So this is what I've done. Now the second step, remember what is the second step we decided? We decided that because this is a ratio data, so what do we need to do? We need to standardize it. We need to have a z-score, right? So there is a command. So I need not go and do a standardization of individual columns. That is what is not required. So what I'll do, there is a command available in R, which is by the name of scale, right? So as soon as like you use the scale command, the entire column, all the columns can be converted into can be standardized in one shot, right? So that command is scale command, right? Right. So how do you write that? That's simply this command. So if I write like this, scale, SCLE scale is the command, right? And I'll write the name of, I'll have my data, right? So this is my data, right? This is the data that I have. And this should be on ratio data, right? Otherwise, I mean, it will not understand what are you trying to do. So if I write this command, what will it do? It will convert all the columns into z scores, right? So we'll have a z1, z2, something like this. And when you are converting z-score, remember what does it use? It uses center as the mean. So the center is used as the mean and the scale is used as the standard deviation. But in my case, so that you know this also, I'm not going to use the center as median. I don't want to use this as the median, as the center, right? I don't want to use mean as the center. I want to use median as the center, right? So I want the median to be the center, right? Why I'm doing it? Because this data is very limited. It doesn't have a too much of a spread. So when the data doesn't have a too much of a spread, it's almost tending towards like a categorical data, like a nominal data. So whenever that is happening, you can use this kind of a, so instead of using mu and sigma for your z-score, you may use a median. And here instead of this, I'll use the mean absolute deviation, right? So what am I going to use? Mean absolute deviation, that is MAD, right? That is what I'm going to use. These two things I'll use, right? So let's look at this. So cars.use, then I go here, I have created this object by the name of medians and apply. Apply, you know, is the command. As soon as I say apply, it is going to, whenever I want to do it on the whole data set, it's apply, use this data set. To means use it for, do it for your columns. If I put 1 here, then it would be for rows, but that doesn't make any sense in this case. So I'll say 2 and calculate median, right? This is what I'm asking the system to do. So let's execute this and see what happens. So I execute this and let me see what is inside medians, isn't it? So if I want to see inside median, I need not type median separately there. I just select median. Look at this. I'm just selecting median here and saying run. And you can see it gives me the median things. So you can see the medians are calculated here. Okay, is there a difference between means? So you can calculate means also. So how do I calculate means? I want to do it in one shot. So apply, and then I'll go for cast.use, cast.use, comma 2, because I want it column wise, and I'll say what? Mean. Okay, so that's what I do. Well, and we can compare, is there a difference out there, right? So is there a difference? Not much, slight differences, that's all, right? But you'll see the median is conservative, right? In all the places the median is conservative. That's an advantage. And at least in number of cylinders. So this is what the theory I was telling you. The cylinders are a very constant number, very limited number, right? 4, 6, 8, only 3, 4 values are there. So you can see here there is a difference, big difference. This is 4.5, this is 5.39, right? So because ideally we should treat cylinders as a nominal data, right? As a ordinal data, not as a ratio data here, right? And so one way of limiting our damage is that whenever you have this kind of a variable, please, you are free to use a median and a MAD in combination, right? Do that instead of using a Z-like thing. Now the question is, can I use different scales for different variables? Like example, for variable number 1, I use a combination of mean and standard deviation. For variable number 2, I use a combination of median and MADs. Is that allowed? Yes, that's allowed. That's not a problem. You can have individual transformations also. But why I am putting it in a single command is because let's say these are 4, 5 variables. This case, this is only 6 variables. Still manageable, but think like when you are working on a 15 variable, 20 variable kind of a scale, things would be really be very difficult, isn't it? So that's why like I'm using this. Okay, so once we have standardized, what is the next step? I mean, logical next step is I need to convert it into a distance matrix. The system can convert it on its own, right? Why I'm doing this is because I want to show you, that's all. The system, when you execute the clustering command, or it gets converted into a distance thing. You need not convert it into a distance first, right? But for showing it, what do? I say cast.dist and I'm converting it into a distance, right? So I get a distance. But as I told you, what does R do? How does it store it? It doesn't store it like a matrix, because the upper matrix is gone. The diagonals also it knows is 0. It's not storing it. So it's exactly, it doesn't exactly store it like a matrix. So if I show you what is contained in this card.dist, it will not look like a matrix the way you are used to looking at a matrix. So look at this. How is it like stored? It is stored in a very, very different way. You can see this, right? You can see this. It's just a lower matrix. You can see, right? The diagonals are also missing. Can you see this? The 1 1 is missing. It starts from 2 1. You cannot see any zero here. It doesn't put a zero. It doesn't take that pain. Why to like waste space? You can see it has put it this way. And if you want to see it like a matrix, that for some reason you want to look at it like a matrix only, so you may say that, okay, I want to have a look at it like a matrix only. This would be a big matrix, isn't it? Because there are 38 cards, so the size of your matrix would be 38 into 38. Not possible to eyeball in the R thing. So but let me just show some portion of it. Later on, we'll see pull out some portion and see it, right? So you can see this is how, let me go at the top, and you can see this now is looking more like a matrix. Okay. So you can see the diagonals now. Do you see the diagonals? You can see this is equal to this. So it has filled in the places for you, and it's showing you like a matrix now because you asked that please show me as a matrix, right? For the system it does not matter. You don't have to like, this is just for showing you. This is for the system. This form or this form is immaterial, right? It doesn't matter what form it is. It can work on anything. Okay, so just for your purpose I've changed it into a matrix. Okay, now we'll start the hierarchical clustering. So we'll do hierarchical clustering. Cars.h cluster. I'm not using any package, right? Just now, what are these dots? These at times when you are copying from a PowerPoint, and if there is a blank space, this is shown like this, right? So cast.h cluster, and I'm converting into a hierarchical cluster. No special package is being used. That means I'm using the base package. What is the base package? You know it. The stuff that is downloaded when you are downloading this R for the first time, right? So those 40 packages, it's a part of that. So H class, so I'm not calling any library, you can see it, right? I haven't called any library since morning. So H class, this is what I'll do. I'll run this. And then I like to see, as soon as I say plot, that means plot on this, I'll get a dendrogram. I want to put a label there, right? So main means that on the top of the thing, this would be the labels equal to cars, $cars, right? So let's look at it. And I can zoom it here. So this is what I'm zooming out. And you can see this cars.distance, and this is default from H cluster. This is the height. So this is a pseudo R square height square kind of thing is given. Now I have to, because this is H cluster. So what will we do? We have to find out the tentative number of cars. That would be a better thing to do. So we'll start from the top. Remember, lesser the better approach. Okay. So we'll start from the top. I see a big jump here, right? Naturally at the top, this place generally will always see a big jump. So I'll see one. If I cut it here like this, cutting here means I'll move my finger from right to left like this, and this is known as the cut. So how many cut I put? 2. So I say 2, and here also I'm getting a big jump. So instead of getting for a 2 cluster kind of a solution, which is very, very restrictive at times, right? 2 cluster kind of a thing. So I'll move my thing here, and I'll see this is how my finger moves. So here I get a 2 cluster solution, and here I'm getting a 3 cluster solution. So I say there are 38 cars. Okay, 3 could be a good reasonable number of clusters. So I'll assume I'll start with 3. So I'll say that 3 is my cluster solution. That's what I'll start with, right? So I'll assume that I have 3 clusters in my solution, right? This is what I'll assume, and this is what I'll start. So I'll tell the system to cut 3, because as I told you, this thing comes from graph theory, and this is because this is a hierarchy, so it is a tree. So this dendrogram is a tree. Now this dendrogram visually looks good if you have 38 members, right? Now imagine there are 100 objects. How will this dendrogram look like? Or imagine if there are 500 objects, then how will this dendrogram look like, right? It will become too much of a hodgepodge, right? Because this size is not going to change. Your screen is not going to change. The screen size is going to be the same. This A4 size is not going to change. So after probably if you have too many objects, then what is going to happen is this may become an impractical approach, right? The edge cluster may become a very impractical kind of approach. So that's why this visual approach of cutting tree may not be a useful thing. So what do? You will have to use some other approach. And I told you one of the approaches yesterday, you can use NB cluster, where you can decide the number of packages. Okay. So now once I put the tree, I like to see what is inside this, right? So I'll just say run this. I haven't executed this command. So let me execute this command first. So I executed this command and I see what's inside. So you see that these are cluster membership. These are total 38 numbers, and you can see they are unique. So car number one is group number one, car number two is group number one, car number three is group number two, so on and so forth, right? Let us make a count of it, right? So the table command will do what? It will tell me the count, how many cars are there in different groups. That's why I use the table command. So table, the results in this. So this is the table, right? So uh, groups dot three. Uh, Giving something wrong. Why is it giving this way? Wait a minute. Let me start from here. There is something. No, there should be three, isn't it? And it's not giving three. So let me execute this command first. Okay. Then let me have groups three, right? This is good. Now let me put a table around it. Yeah, it's fine. Okay, so fine. It was correct, right? This is cluster number one. This is cluster number two. This is cluster number three. So the first cluster has 7 cars, and this should all total up to 38. I was trying to add up, and I was not adding them correctly. Suddenly I realized. So 7 plus 5 is 12. 12 and 26 is 38. So all the items should be accounted for. You cannot have something which is left out, right? So 7 plus 5 is 12, and 12 plus 26 is 38, right? So first group has 7 cars, the second group has 5 cars, and the third group has 26 cars, right? So this is what it gives me. And the third group is very large. You can see this, right? So it has 26 cars, right? This is what we see. Now let's do one thing. Let's simulate a 2 to 6 kind of a cluster thing. So what have I done? A small function as apply. Number I want is 2 to 6, and I've written a function that is the number of clusters. So number of clusters, put a table for what? That we'll put cut trees on cars.hclust. Take this cars.hclust and keep on putting and to keep on telling me the numbers in the different groups till the time this NCL value is satisfied. So the NCL, what are we giving? We are giving this NCL as 2 to 6. So these values will become 2, 3, 4, 5, 6, right? Like this. So let me show you, and then probably you can see what is that we are doing. So we are putting names also on this, and this is what we get. Okay, so let's have a look at this. So what it is telling me, if you want 2 clusters, then your cluster solution will look like this, right? 1, 2, right? So your cluster solution says there should be 12 cars here, and there should be 26 cars in the second thing. And as soon as you say, so remember the example that I'd given you yesterday, right? The example that I'd given to you yesterday was that let me run the codes once again. Why? Because I doubt I haven't removed the initial two columns. I think I made a mistake, though I was discussing with you, but I haven't removed the 2 columns, right? So let me rerun the codes again, right? Just for surety. Just give me a minute. So I'll select everything and just run it. So from here to here, I'll just rerun this again, right? Let me clear this space first. Okay, and I'll run this entire thing again. Okay, so that I'm sure. Yeah, I made a mistake. Very clear, right? Because my cluster solution is coming different. And why this happened? Why the third group? So this is what I was telling you. I didn't remove what? I didn't remove the first 2 columns. Because I didn't remove my first 2 columns. So did you see what happened? The third column, the third cluster had 26 cars. So that's what I was telling you, that if you don't remove your column which has too much of unique values, then what will happen is that you'll so there was a cluster which got probably a very large, right? Or the other clusters were very small, or the opposite can happen where you have too many number of clusters and all those things, right? So that's what the problem. So now what we have done is that this is the cluster solution 8 20 10, and now what I'm doing is I'm asking it to simulate a cluster solution of 2, that if I put a cut on 2, then what will happen? If I put a cut on 3, what is the membership I'll see? If I put a cut on 4, if I want 4 clusters, 5 clusters, then what will my solution look like, right? That's what I'm doing. So that's what I wanted to show you. Now this is where we are. Now remember the idea that I told you, isn't it? If you look at large countries, there are always fringe groups who always keep on saying Azadi chahiye and all that stuff, right? That we want to go away. That is always there, right? So if you keep on allowing for space, then what will happen? Fragmentations will keep on happening. Now we'll use this method to understand whether a cluster is stable or not. What is a stable country? What is a nice integrated society where nobody wants to part away, isn't it? Even though you give them a chance, right? That's the important. So even if you give them a chance, they'll not part away. That means it's a cohesive kind of a country, a integrated country. So the test of a country is give people chances to part, and let's see how many part, right? So similarly in cluster, we will use the same approach, that we'll look for a 2 cluster solution. So it says 18 and 20. Now what will I give? I'll give a chance and say, okay, I am allowing for 3 clusters. So guys who are not satisfied, who feel we are different, can remove, can get themselves isolated and can join the third cluster. And if this breaking, some breaking will happen, there will always be fence sitters, isn't it? Some people who are sitting on the fence and are not clear about where they belong to, those guys can separate. I mean, some small fragmentation is okay. But if there is a large fragmentation that happens, then you can very well conclude that the cluster definitely was not a stable cluster, right? So you have to understand that. So when I do a 2 cluster solution, this is my membership, right? 18, 20. I'm not using any sophisticated metric to prove that we have stable clusters or unstable clusters. What we are using right now is a common sense based approach. And believe me, this works. This always works for me. That's why I took the case first. And when I give it a chance of cluster 3, look at the first cluster. What happened? It gets partitioned almost down the middle. 8 here and 10 here, right? It just gets partitioned down right in the middle. So that means if I would have chosen 2 clusters, I would have ended up in having a very highly unstable cluster. That is 1. And the cluster 2 is very stable, though it is a large cluster. You can see it is 20, it remains 20, though I've given a chance to its people, to its member, but they don't like to change. Okay, so this was an unstable cluster, this was a stable cluster. So good that we have moved from 2 to 3. Now let's give it one more chance. So we give it a chance of 4, then what happens? The 8 remain 8, the 10 remains 10, and 20, there's a marginal breakup. And I told, if you keep on giving chances, then the cluster has to be populated. Remember, no, if you give chances to people, then the land will always get populated, irrespective of what you are giving, isn't it? If you look at this place, Egypt and Israel, they have a huge desert in between by the name of Sinai Desert. But the wars are being fought just to retain that Sinai Desert. So always remember that land and space are always to be occupied, right? Though they may be useless or useful, that's a different thing. Okay. So this is what, right? So some disfragmentation happens. So I'll say 3 is a quite a stable kind of a thing. And if moving from 3 to 4, does it make sense, right? So does it make sense? Let's fragment it further. Let's see, if I move from 4 to 5, what happens? If I move from 4 to 5, now this 17 thing breaks a lot. You can see the 8 is stable, the 10 is stable, the 3 is stable, but now this 17 actually faces fragmentation, and there's large fragmentation that you see. So 5 definitely is a fragmented solution. And then if I go to 6, then let's see what happens. 8 remains stable, 6 remains stable, 3 remains stable, and this actually then fragments in the middle, and this becomes 5, 5, right? So the lesson is that if you keep on giving scope, then your number of clusters definitely will keep on increasing. That is going to happen. There is no doubt about it. And as I said, the cluster solution lies somewhere between 1 and 38. That's the reality. So, and lesser the better. So these two rules we'll use, and we'll say, okay, I think 3 is good enough for us, right? So 3 seems to be a good enough, right? I'm saying good enough. Now, if you ask me, how is it that good enough? So I've given you a very subjective story out here, right? That's not wrong, I'll again say, but it's subjective in the end, okay? So this is how I decide on the number of cluster. Now, as I go ahead, and then the question is, do I live with this subjective story only, or is it something else that we can do and understand that, okay, okay, this is fine. So we'll do something when we go ahead and put some numbers also to it. Okay, so so now that we have accepted that there it should be three cluster kind of a solution. So what we look at, we say that, okay, let me have a look at this three cluster solution. Okay, you know, this double equal to means what? This double equal to means is a logical equal to. And what I'm saying is, tell me the cars according to the groups in the cars.car means this is the car model, right? Tell me the car models which belong to different clusters. So let me run this, and this is what you get, right? So in the three thing, the first group, the first cluster contains these cars, right? I don't understand any of these models. So if you understand it, you can make some, probably you can conclude something, but I absolutely do not know anything about these models, right? And if I want all the cluster solutions together, right? I want that all the three clusters, I want the names of the models. Then this is a small function which is written unique groups dot three function g cars dot car group car. So show me for all the groups, right? This is what I'm doing. So if I run it, you can see the models which are written. So the model wise. So the first group, so this is the first group, you get the first cluster, and this is what it contains, right? Then let's look at the second group. The second group comprises of all these cars, right? And below, if you see, it says that actually there are 38 cars, and this is the second group out of it, a subset of it. And this is the third one, right? So this is how the cards are divided. You had seen that there are 10 cards right here, and there are 20 here, 10, 20, and then we have 18 here. You can 8 here, sorry, not 18. So you can see 7, and this is 8. Dodge, Cent, Regis, right? So these are the cards that we have. So you see this. Now, as I said, like as we discussed yesterday, a better strategy is always to start with what? Hierarchical clustering, and then look at the solution by using PAM. Though I have put cut and all those things, but we'll simulate the solution for. In the earlier thing, I was not simulating different cluster solutions. What I was doing is I was just changing my cut. In the hierarchical thing, I was just changing my cuts. That is all that I was doing. But in the PAMS.car, I actually changed the cluster solution in C, right? So hierarchical followed by PAM, right? Here the command is PAM. I'll need to have a, so we'll discuss what a PAM is first so that you are clear what a PAM is. So now we are going to use a package, though I'm not put it here because at the top, if you where I start these codes, I've attached that library, right? The library cluster would be somewhere here. I would have attached it somewhere, right? So that's why it's not seen here. I've attached a lot of libraries, and this would be one of it. The cluster would be one of the libraries that I would have attached, right? So you can see PAM also I've done earlier, so I would have attached it. So I'm attaching the library here. So I'll open it, and we can have a look at the library also. So this is the library, bread and butter library for clustering, and we say cluster. Let me also open. Uh, sorry. Let me open what this cluster library is. So let me go here. So I'll just say cluster package, because here it is package in R, and you know that there would be a PDF that will open up. So I'll just open up this PDF, spend a moment on it so that you are familiar with what all stuff this can do. So version is this, the date, very current, right? 3rd October it has been defined. And this is based on a book, Finding Groups in Data, right? So this is the book, Cluster Analysis Extended. Roseview is the one, he is the one who has contributed a lot to the idea of clustering, and it is based on his book, right? So this book was given by Kaufman. Kaufman is one of the leading authors as far as the clustering is concerned. And Roseview is his co-author. 1990, they wrote a book by the name of Finding Groups in Data, actually, right? And it says this is what it is, okay? And imports graphics, GR device, stats is our base package, right? Utils, these are the dependencies, and you can see that these are the authors. These are the authors who contribute to it, right? And this is what we get. Now, what all things it does, if you look at it, you'll see names like English female names like Ignis, you'll see Clara, right? So these are all algorithms. Ignis is agglomerative nesting, right? Nesting means hierarchical. So nesting is also hierarchical things are known as nesting because one gives rise to the other, right? So that's why it is nesting. So agglomerative nesting. So this is agglomerative clustering. Ignis, and I said they are like female, English female names. If you look at it, Clara, Daisy. Daisy is your distance matrix, right? Diana is the divisive thing. Fanny is your, what I told you, you can do a fuzzy kind of a thing. So this is Fanny, right? Then you have Mona, right? Then you have Pam, partitioning around medioid. This is what we are using right now. We are using Pam right now, right? So a lot of probably then there is something known as a Silhouette that we'll discuss, right? So that this is a measure. I told you 30 measures yesterday. 30 metrics are available to establish the number of clusters. So Silhouette is one of them, and Silhouette is really robust, right? I really like Silhouette, right? So that is one more reason why I use PAM, because PAM reports the Silhouette thing. So this is an overview for you for the cluster package. We are going to use 3 of them. We will use Ignis. We'll do Daisy here for distance. We'll use Clara here, right? And we'll also use PAM. PAM we are using right now. Mona is for binary packages, right? And this is PAM, and it also has a data set by the name of flower. You can see this, right? So there is a data set also here by the name of flower. I'm not doing Fanny. If you want, you can open this and you can look at this package and experiment, play around someday, right? That would be good. And you know the beauty of our package is all the data, examples, everything is included. So you don't have to hunt around for data set. The codes are already given, the data is given, right? Data agriculture, and then everything is done. So if you want to actually play around with this, you can do that, right? So now we are going ahead and we'll do a PAM. PAM is nothing but a k-means clustering. So if it is a k-means clustering, then I have to give it the number of clusters, right? That is very, very simple. So I have to tell the system that this is the number of clusters that I want. Okay, isn't it? Then only it is, sorry, gone too far. So this is what I'm doing right now. And PAM stands for partitioning around medioids, right? It is not partitioning around means, though PAM, if you expand it, it can also mean partitioning around means. So it is a k-medioid method, not a k-means method. What is the difference? That is a subtle difference between a k-means method and a k-medioid method, right? So let me explain it to you so that you understand what does it mean. Okay, so let's look at this space, right? So let's say I'm making 2 clusters. Okay, let me have a simpler case. So these are the kind of cases. This is one group, and I have another group, right, which is like this, right, which is like this. So if I need to have a cluster solution, this should become one cluster ideally. This would be cluster number 1, right? And what would be this? This would be the second cluster. This would be the second cluster, right? So this is cluster number 2. So there are 2 clusters here, cluster number 1 and cluster number 2. Now what will happen is when your clusters are very large, you will have to make sense of those clusters. Or think of a situation where you have clusters, but they are to be communicated to your business counterparts. Your business counterparts will ask for a actionable kind of a thing. So what we are going to ask is that can we have something which is actionable rather than like putting it this way. So actionable thing means you'll have to give some definition to this cluster, right? Isn't it? So this, like example in telecom, somebody may define one cluster, one segment of clusters, and dynamic the professionals. This could be a name. Now, how do you arrive at this description? Dynamic professionals. So dynamic professionals will mean probably the people have looked at their job history, and you see a lot of changes. These guys keep on changing their jobs after every 1.5 years. So probably they're dynamic in nature, but they've always been on a job. So for that, and they've been with good companies, let's say. So you look at these two attributes and you define it this way. So that means ultimately the clustering should lead to a personality kind of a thing. Why a personality kind of a thing? Because business is the end user of it, and they should understand what are we talking about. At times people go too far ahead and give them very, very fancy names, right? So as data miners, our job is not to give very fancy names, right? It is to give names which actually make some sense. So you do some kind of a profiling, and that is the reason that I have hold back the country thing also. So whatever cluster information is available, I'll mix it with the country information and make a profile kind of a things, right? Now, what are the kind of things that I can look at this? I can look at the mean of the MPG. If the mean of the MPG is higher, that means they are gas guzzlers. And if the mean of the MPG is low, that means these guys do not, they are fuel efficient cars, right? And if I as I said, that if the drive ratio is high, they are probably meant for city driving, and if the drive ratio is low, then that means what? Then they are racing cars or something, or high performance cars, right? So these kind of things I'll have to look at, and then I'll have to understand that okay, this cluster is of this nature, right? So what am I doing there is I'm taking averages of all the values, right? So that is what, and you'll see averages. So for every cluster, you'll see this kind of a thing. I'll have cluster one. Let's say I have three clusters. So I have cluster one, I have cluster two, and I have cluster three. Okay, these are three clusters which are there, and then I'll have variable one. This is variable one, right? So this is one of the strategies. Remember this, how to do it. I had written a paper, academic paper, which got published. In that, like, I'd use this strategy for cluster profiling. Okay, so this is, let's say, variable 2 here, and this is, let's say, variable 3 here. So how to make sense of your thing? So what you can do is, this is variable 3, so and so forth, and this is variable 4. So taking averages also may not mean anything. So what we do is, generally what I do, instead of taking averages of variables and populating them here, and then it may not make any sense if the variable number is higher, what I generally do is, I look at a variable v1, I calculate the range, right? And using this range, I divide the values into three portions. And that's very, very intuitive. I say low, I put a cutoff for low. Then the second one is a medium value, and then I put a high value, right? That makes sense. And how is this high, medium, low arrived at? Just divide the range into three parts. So what will I have? This may be a high value. This may contain things with high value. This may contain things with medium value. This may contain things with low value. And I can give it a color code also, that high would be red, medium would be yellow, and L would be green. Let's say I'll use three colors also, right? So imagine I'm using three colors. And then let's say this is medium, this is high, and this is low. So what will happen if you look at the colors? A heat map kind of a thing will emerge, that this particular cluster is high on these aspects, medium on these aspects, and low on these aspects. And from there you can define your cluster, right? So this process is known as profiling, right? So there are many approaches which are possible. Okay, so two profile clusters, right? So this is one, that your cluster needs to be profiled if you really want to communicate them to business. But because we are all data scientists, so we may not profile them. We may just say that, okay, we have made a cluster and that is enough. How does the k-means actually work? We have to understand it this way. Look at the algorithm, right? So I'm going back to the algorithm. K-means, if you remember, how was it working? Let's say these are the three classes to be partitioned, and I've given k equal to 3, assuming, because there are three classes there. So these are my three classes, and this contains circles out here. So it will start with the centers. So in a k-means, what happens is, the center is, let's say the plus is my center. So it can decide any center, right? Plus, a plus here, plus here. So the center may not be an object actually, right? Now this scale, this is very funny. I mean, if you look at it, right? Because in terms of objects, don't you think the center should be some object, isn't it? I mean, can you take a average, or can you take a middle point of a Dodge Regis and some Audi 500, 5000? That will not make sense, because actually, practically, really, that thing is not existing at all. So what does K medioids does? K medioids puts a condition. It says, and that is why it becomes a bit more practical at times when you are handling things like cars or something like this, right? Some objects. So what will K medioids do? It will force to choose the center as one of the elements. It will not allow a imaginary center to be chosen. So it will say either choose this, so you choose this, this becomes your center, this becomes your center, this becomes your center, right? And finally, when we get a solution, the advantage is it will give me a representative car, right? So it will give me a representative. So if I want to understand the cluster, I need not do a very complicated exercise. I can just look at the representative and I can very easily conclude that probably this is the kind of cluster we are looking at, right? So that's what a K medioid is. So the difference between a K means and K medioid is that the K means will, because it works on an average kind of a thing, so the average can lie anywhere, isn't it? The average of 2 and 3 is neither 2 nor 3. It is going to be 2.5. But we have discussed median is a positional thing. So the median, it has to be some value. It will generally not lie in between, isn't it? Until unless if you have even numbers, that's a different thing. But in this case, in this algorithm, the median is forced to be one of the objects. Okay. So that is there. Now let's run it and see what is happening, right? So this algorithm is known as partitioning around medioids, or PAM in short, right? So PAM and cars.dist, I'm using the distance matrix here, and I'm saying please give me 3 clusters. This I have to provide every time, right? So I'm saying 3. Executing this command. Also, I'm trying to look. You can say str here, or you can say names, whatever you want to use, right? So if you use this command, they are the same. Str cast.pam is the same thing, right? It's the same thing. You can use this or you can use this, right? They are the same thing. I'm not using both of them. So names, so it will tell me what all is contained inside. So I'm executing this command, and you can see it contains medioid information. It contains the ID of the medioids, the clustering information, the objective, what is the objective, isolation. Some of them you may not understand. Example, isolation, call is very simple. Sil info, this is the sil out info. Dissimilarity, so we can look at some of these, right? Let's say example, cars dot pam, right? I put a dollar sign, right? So I'll put a dollar sign and say medioids, right? If I type the spelling wrong, it will go. I'll choose this and say enter. So it says that this is 28, 22, right? Something like this is your medioid. Or I can look at these things, the other things, id dot medioid. Let's look at id dot med. So these are nothing but your IDs, and your these things too will always coincide generally. So your 20th car is the representative of first cluster, the 8th car is representative of the second cluster, and the 22nd car is the representative of the third cluster. This is what it means. Okay, so you can see all this. Like example, if you want to look at the dissimilarity, this contains the dissimilarity. So the cars dot pam, let's say I look at dollar and then DISS, dissimilarity. When I look at this, then it hasn't created a dissimilarity matrix, right? In some cases it is not generated. Okay, so you can just like, it's not many things are useful here. I'm just showing you what all is contained inside. So this is your call. So you have given, call means the formula that you have used. So this is your call, right? Okay, so this is what all is contained inside this objective, or this object. So let's look at the 3 cluster solution provided by PAM, and let's compare the 3 cluster solution provided by what? The hierarchical thing. Is it similar, or is there a difference between them? Okay, so we are making a table of groups 3. This is our hclust solution, and cars.pam clustering is the thing that we get from where? From our PAM thing. So I run this, and what do we see? That cluster 1 in this case also 8, this also 8. They don't agree on the second cluster. PAM says there should be 19 objects, whereas hclust said it should be 20 objects. For the third cluster, PAM said it should be 11, and your hclust said it should be 10, right? So there is difference of one thing, and these minor differences can come up. Let's not worry. So PAM and almost the hclust things are almost like in unison, right? They are giving me the same kind of a thing. Let me do a plot. Why I'm doing a plot of cast.pam is because I want to look at the sellout thing. Sellout is, as I told you, one of the robust metrics. So out of those 30 methods, sellout is there. There are many. When we do that NB class, we look at those 30 things. So we are addressing the first one, which is the sellout thing. So let me execute this command and have a look at this. So you can look at this. Now look at the information that is contained here, right? So there's a sellout plot. Why do we call it a sellout plot? Because generally in dark, if you look at a city from far away, then you'll see the outlines of the buildings, isn't it? If you look at a person who's standing in the dark, you'll see the outline. So these are like kind of outlines in the dark are known as sellouts, right? So that's why it's known as sellout. So this says there are 3 clusters, CJ, n is equal to 38. You have 38 objects, and this is your call. You use the PAM, k equal to cars and k equal to 3, n equal to 38. There are 3 clusters. The first cluster has 8 cars. This is fine. And what is this? What this one that is given here? It also says, well, let me have the drawing thing. This says that the sellout width for this cluster is 0.78. Now the question is, how do I understand this 0.78? So sellout width generally are read like this, or you can call it sellout coefficient, whatever you want to call it. Some people call it sellout width, some people call it sellout coefficient. So here we call it sellout width, right? Some people may call it sellout coefficient also. So how do we read it? Anything which is greater than or equal to 0.70 is a good cluster, very reliable cluster, stable cluster. If it lies between 0.5 and 0.7, it is a okay kind of a cluster. 0.69 probably, right? So if it lies between 0.5 and 0.69, it is a okay kind of a thing, not very highly reliable, right? And 0.5, 0.4 to 0.49, I mean, it is a very unstable kind of a cluster solution. It's very sorry, this should be 0.49. Yes, is a very unstable kind of a cluster, and anything which is below 0.4 is absolutely not acceptable as a cluster solution. There is nothing in the world where anything which is less than this, which is if this is greater than any class SC, then this is not at all acceptable. Not at all acceptable, right? So let's look at our cluster quality. So this says 0.78 is a good cluster. We are happy about it. This says 0.64. So I'll pull out some paper which say no, 0.6 is also a good cluster solution. So I'll start pulling out those papers and prove this is also a good cluster. And business is a very different thing. It's not the ideal world. So I'll start using these logics and prove that this is my good cluster. This 0.51 is unstable cluster, right? Then this will always happen. When you're doing clustering, always remember 1 or 2 of your clusters would be miscellaneous kind of a thing, where the logic is more of because it doesn't belong to cluster number 1 and 2, hence it belongs to cluster number 3. So good clusters are where the membership is very clear. We belong to this cluster, right? That's the thing. But miscellaneous clusters also do arise, right? So that means poor clusters. So and typically if you look at a cluster solution where you have 10 clusters, 20 clusters, you'll find a couple of clusters or 5 clusters which are miscellaneous and which might have a very poor kind of a sellout thing. And what is the overall average? This is the overall average. So how do I conclude whether what kind of a cluster exercise I've done? So 0.63 is a okay kind of a thing, isn't it? I'll say okay, fairly okay kind of a cluster. This is what I also remember that when we are working with clusters, if I get a mix of very stable clusters and unstable clusters, what I tell the business is I'll say I'll only take these two clusters. I'm sure about these two clusters, right? And I guarantee that this is going to be a very good solution. This is a very good solution. And this is like throwing darts in the dark. They may hit or they may not hit. So on 11 cases, I don't have a very, let's say, good solution. But on 27 cases, which is the larger number, I have a nice clustering solution. Okay. This is the weighted average. Weighted average means what? 8 multiplied by 0.78, 19 multiplied by 0.64, 11 multiplied by 0.51, and then divided by 38. So you'll get this, right? Overall, what is happening. So when the average cluster width is less than 0.5, don't propose all the clusters. Say these are my stable clusters. Separate them into very stable clusters and non-stable clusters. So this, for these groups, the marketing campaign, please roll out with confidence. It's going to work. For rest of the guys, it's up to you. How do you want to treat them? I'm not sure. If you want to take a risk, you can take it. And if there is a lot of financial liability that is probably there, then you may just roll out a uniform campaign for every other cluster. For the unstable one, we can just have a uniform program. If it hits, it hits. If it doesn't, don't worry about it, right? So this is the strategy on how we work on clusters. Okay, so a lot of strategies have to be used, isn't it? Though this is a very simple thing, but this is what is happening. Okay, so this is what we have seen. So before we go on a break, let's finish this stuff also. Cars, dollar cars. What do we get here? So this is like some kind of membership that we'll see. So what we are doing is, what we have done here is, can you tell me which cars, which was actually a part of group 3, was not a part of this? So which doesn't tally in the groups 3, and there was a difference in the PEM thing. You saw one of the cars was actually the one in the second group which was not telling. So Audi was the confusion case, right? This car, Audi 5000, was the confusion case, right? And what are the representative cars? If I want to understand these 3 clusters, I can go to the medioids, right? So for the first car, if I understand what a Dodge Cent Regis is, I can understand what cluster 1 is. Similarly, like Dodge Omni, if I understand it very well, I can understand what that Dodge Omni thing is, right? And for Ford Mustang Ghia, if I understand what Ford Mustang Ghia is, then I can understand what this thing is. So we can profile them. I'm not doing the profiling right now because I like to cover the other codes also. And there I've done some profiling. So there is no need to do profiling 2 times. You can actually, when I go through the profiling exercise in the other codes, you can use a similar profiling exercise for the cars thing and see what happens. Okay, so there's no point in repeating things. So we'll take a break, and now we'll start from the top, and we'll look at other things also. So right now what we have understood is that though clustering is a very easy thing, but you have to combine the use strategy, isn't it? There are lot many things there. Example, there is a difference between a means and a medioid. There is a confusion regarding the number of clusters. So this is how I work. So I have to do lot many things to ultimately tell that, okay, yeah, I mean, yes, this is a good cluster solution. Also, I said you have choices of the distance metric, right? We have been tested that really. So what happens if I change my distance type? What happens if I change my linkage? Will the cluster solution change? So all those things we'll try to experiment in this half now, right? Right. So with one example, and how do I test? Has the cluster solution actually changed, or is it the same cluster solution? So all that kind of stuff we'll do in this half, right? So now what we are going to do is uh, getting more familiarized with clustering. Try to address those couple of things like what happens if we change the distance type, this and that, right? So that's what we are going to do for the next whatever time is left. Next 1 hour. So we have this library, which is a specialized library by the name of DND extend. EXTEND. The full form can be dendrogram extended or something like this, right? And in this case, what we are doing is we are going to use a very simple data set, which is the US arrest data. Now this USA arrest data is actually a data about 4-5 very serious kind of crimes, and it is collected all across the US 50 states. So the 50 states and the data pertaining to them, and it's about the serious crimes. Okay, and I think this data is a part of DND EXTEND only. So I'm attaching this library, right? And then we have USA arrest data, and I'm giving it a name so that I can use it. So I'm saying that this US arrest data, though I have this data set, I'm giving it some name, because if I give it some name, then it's easy to use, right? So I'm just giving it some name. And if I want to look at this data set now, then strf, I'll see df, right? strdf. So let's look at this. What do I get? So these are 50 observations, I said, because these are 50 states, and there are 4 variables which are very serious kind of crime: murder, assault, urban pop, and rape, right? So this murder is about physical safety, right? Assault is also about physical safety. This is women's safety. The last one is women's safety. And urban pop is like burglary. So this is about the asset safety. So these crimes are related to 3 dimensions, if you look at it, which define the character nature of a city or an area. What about the personal safety? What about the asset safety? What about women's safety? Isn't it? That is what define an area. So that's why these 4 variables. That's the idea basically. Now, yeah, probably we discussed that. Yes, we discussed that. If the data is of different measurement levels, then we need to standardize or scale the data. That we definitely discussed. But if the data has missing values, then also there can be issues. Like k-means will not work if it has missing values. So we need to omit the missing values. If you have large kind of a data set, and if you can afford to, and clustering is not a very data intensive exercise. So in clustering, thank God, the requirement, the data requirements is not very high. We did a clustering on just 38 rows, right? So the number of sample size here, there is no requirement of a very high sample size, right? So what we do is we just use this command na.omit. So what does na means? Wherever there n is, what action to take? Omit. Omit means that it will, if there is one na in any of the variables, it will omit the entire row, right? So by chance, if this data has anything, then the number of rows will become less. So let me use this. I do not know if there are any NAs or not, but I'm straight away using this command, right? I use this command, and then let me see, have the number of rows decreased? If the number of rows decrease, then definitely it means that it has this anything. So I'm just checking, I'm doing str again, and I see there are again 50 observations. So that means the data did not have any kind of a NA means missing kind of values, right? Missing values are a very serious thing. Regression also you can't use them. Clustering also you can't use them. So at times you omit it, at times you can impute it. You can impute it by medians if you want. Generally, is a safe thing. So now this data is free of any NA. That's what we have ensured. And now what are we doing? We are going to scale it. If I use the scale command, I told you what it is going to do. It's actually going to calculate the z value, and the z value means that my center is going to be mean, and my scale is going to be my standard deviation. So I'm just doing this. And if you want, you can have a look at the data set. Head means a sample 6 of it, and you can see that all these values are converted. And we have discussed it many times. Generally, the values will lie between -3 and +3, right? So that's what we see. Okay. Now we are converting. So I'm having this object dist.euclidean. So I'm making converting this data set into a Euclidean distance based matrix, right? So I dist is my command, and always remember dist command comes from the base packages, right? It doesn't require any special library as such to calculate this dist. So I'll say df and method equal to Euclidean, right? So Euclidean, I'm clearly specifying. If I don't specify, by default also it will use Euclidean, right? So we take this and then we execute this Euclidean, right? Now, if you want to see this, you can see how many digits, 7 digits it's showing. So what I do is I don't want to look at 7 digits. So I'm using a round command, that whatever is inside this should be rounded to 2 decimals only. And the other thing is, what I'm doing is I'm saying that distance, you know that the distance dot Euclidean is actually not in the form of a matrix. So what I'm doing is I'm telling it to put it like a matrix and only show me the 7 by 7 part. Otherwise, this is a 50 by 50 matrix, isn't it? Now 50 by 50 matrix I cannot see. So I'm saying just show me the first 7 columns and rows and round them to 2 decimal place so that they are not like this. Can you see this? Whole bunch of, like, let's say 7 digits are there, 8 digits rather. I don't want to look at a eight level of decimals. That's not useful. So this is what I do, and you can see this. There are 7, 1, 2, 3, 4, 5, 6, 7, 7 this side, and all of them are two digit. There are 2 places of decimal. That's all. 2 digits after the decimal. Okay, so you can see a 7 by 7 out here neatly. So this is how the distance matrix is 0, 0, 0. You can see that we have done. Okay. So now what happens? This is all ratio data. You may say that, okay, we have dealt with ratio data. Now what if this is a mixed data? What happens to the distance matrix if it is a mixed data? So let's work on a mixed data also.
So,
This library.
Amit,
Yeah.
Amit,
Yeah.
how do we read it? Means what we have concluded here in this
The
matrix.
distance matrix. This distance
Yeah. So
matrix. So what
what
we say
basically
is,
we have concluded? Yeah.
oh, okay. So what I can conclude is that the distance between Alabama and Alaska, based on these 4 crimes, is 2.7, and the distance between Alabama and Arizona, based on these 4 crimes, is 2.29. So I can say that Alabama and Arizona are nearer or resemble more in terms of these 4 crimes. Either both of them are high on these crimes or both of them are low on these crimes. Or I'll look at this one. Alabama and Arkansas, if you look at it, this is 1.29. So I say that the distance between Alabama and Arkansas is 1.29. That means they are very, very near to each other, right? As compare, and look at this, California and Connecticut, if you look at it, the distance is 4.07, which looks big if you look at the scale on this. So that means California and Connecticut are very, very different if I look at this crime profiles. So that means one of them is probably a safe state and the other one is an unsafe state, relatively unsafe state. This is what it means, right? And if you ask me,
And,
do these, yeah,
and to conclude, then we have to go back to our base data actually
yeah,
to see.
exactly. You have to do that because this is made on what? Again, coming back to that, this distance matrix is based on what? This is based on the standardized data, right? So then you'll have to go back and do all those things. We'll do all those things, don't worry, right? But we definitely get an idea which states are like similar. At times you don't need the actual thing, right? You just see relative things, that these clusters are similar, and you very well get an idea that these are like high crime places, this is a low crime place, these are safe kind of states, these are not safe kind of states. That you definitely get an idea. Okay. So uh, all sort of combinations are possible. Ultimately depends on what you want to do, for whom are you developing this solution, all those things become important. Okay.
I'm just looking at this table. Can we conclude that, say, if we say this California and Connecticut case, so can we say that California is has more crimes than Connecticut because
No,
this is
no, not
distance?
looking at this. Now, it could be the reverse also. I mean,
Yeah,
Connecticut
could be
may
the
be
reverse.
the
That's
higher
what I'm
criminal
saying.
thing. Hmm.
Yeah, so that's
So
what we. That's why we need to go back to our base data, I think.
go back and look at it, right? Because here I'm not
Yes.
clear. One, I definitely, what I can
Yes.
conclude, one is criminal and the other is not so criminal kind of a place. So just looking at this distance matrix, I cannot definitely conclude which is more criminal, which is more, let's say, this thing. Somebody who's living in US might straight away have an idea because He's living there, he goes through news and all those things, may have an idea. Like example, as soon as we say like example Bihar and let's say Gujarat, we have that information. The distance would be higher, and we can immediately say that yes, there is a logic to it, right? So, but looking at the distance matrix, we cannot say. Some more information is required. So this library, I've already done it. Now let's look at what happens to the mixed data. So I'm attaching this data flower, and you had seen this data is available as a part of this library cluster. So I'm attaching this data set, which is flower, and I'm doing a str of it. So you can look at the what is inside it. So it is 18 observation. And if you want to go into the details of what this flower data is, you can go to the cluster package, right? We had opened the cluster package, if you remember. I closed it, I think. Yeah, it's still open. So you can go to the flower thing and have a look at this data set, right? So this is a flower data set. You can go here and you can see what it means. So it means V1 is winters, is binary, whether the plant may be left in the garden when it freezes. So can it be left out in the cold? V2 says that you know that some of these flowery things, they need to be in the shadow, not in the direct sun. So that is thing. Tubers, you know, plant with tubers, right? Like example, cactus is a tuber kind of a thing. So this is like colors. There are 5 kind of colors: white, yellow, pink, red, and blue. Soil, I mean, what kind of soil is required? Normal, wet, or simple soil, dry, normal, wet. So these are the codes. Ordinal means preference, like it's people preference. So the rankings are given 1 to 18. I know this is a crazy scale, 1 to 18. I mean, who will give this kind of a ranking? And this plant's height in centimeter, right? And this is now interval scaled. That means the distance that should be left between the plants, right? So it's a mixed data by all standards. You can look at it here. So the same thing here, right? And this data set, as you can look at it, it has been provided by from this book, right? Style of Hubert and Rossio, 1996. And this is because they would have proposed this Agnes algorithm there, and during that they would have used this data, right? So it has been picked up from a academic paper. So V1 is factor data. These are all factors. These are ordinal factors, ORD dot factor with 3 levels, right? And these are 18 levels because they are preferences, choices. So the first is the best preference, is the least preference, and 18 is the highest preference. These two are numbers because this is the plant height in centimeters, how long they grow. And this is the minimum distance that should be maintained between the plants, right? So this is how like the data is. So we are just trying to convert it into a distance matrix. So now we are using this DAISY command. DAISY and DIST are the same thing, right? Remember that. So if you are doing a Euclidean, uh, DAISY and dist will result into the same thing, because earlier we used dist, and dist I told you is a part of the base package, right? We use the dist command, right? This is the dist command. This is for converting into a distance. Now what are we doing? We are using a DAISY. DAISY stands for dissimilarity matrix, right? So this is DAISY here. Now I'm not telling it any matrix. Can you see this? But as I told you, R is intelligent. It will straight away start using the Gower matrix. So let's run this. Right, it was a mixed data. And I'm doing the same thing. I'm rounding it off. I want to look at this DD thing, only 3 by 3. That will give me an idea, and round it off to 2. You can look at 4 by 4 if you want. Okay, I'll do it 4 by 4 if you think 3 is too small. So look at this 4 by 4 stuff, and then we can run it, and you can see this, right? Can you see this? Do you see a distance more than less than 0 or more than 1? You don't see it. Why? Because the Gower matrix treats this as a, everything is converted into a factor data. So the Gower algorithm will have something which will convert the ratio data into a categorical data first, and then it is going to convert it into a distance. Then it will use some kind of a matching thing and it will convert into a thing. And that's why you say all the values lie between 0 and 1. That's what I told you, right? So this is what you see here. Now let's attach some more libraries and do. So this is about the distance thing. You can clearly see that the distance command, and if you do it through gover, then this is what it results into. The command remains the same, but the choice of the matrix changes things. So if I choose a gover, the distance matrix will have values which will be between 0 and 1. But if I don't use gover, I use Euclidean, then what is going to happen? The distance matrix can have any kind of values, the way like you looked at it in the USRS data. So library facto extra, ggplot is more of a library for plotting. It's rather a framework for plotting, which has been accepted as a package. Right now, DIST Euclidean, do you remember this? This is going back again to my crime data, right? Just to remind you, DIST Euclidean is nothing but my distance matrix based on Euclidean. This is the US crime data that we are talking of. So what do I do there? I'm using this command fviz underscore dist distance dot Euclidean, right? So let's see what happens here. So what do we see here? So the distance matrix, because these are 50 cities, isn't it? So if I write numbers, at times when your number of variables becomes very, very large, then the numbers don't make sense. Reading numbers may not result into anything. So it is better to convert it into a heat map kind of a thing. A heat map visually can give you an idea that which are the states. The dark red, the brick red will mean they are absolutely close. That's why you see the diagonal. The diagonal here is not coming from up to down. It's going from the bottom corner to the top corner. So you can see the diagonal is very clearly visible. Brick red, it's brick red, right? You can see the diagonal very, very clearly. So anything which is like a brick red is near, and anything which is dark blue is farther apart. So you can see this bunch. So if you look at this state, like example Iowa, and if you look at this Nevada or California, they are far away. And California, we know, is a very populated area, right? So California should be a more let's say criminal kind of area. So that means Iowa would be the safer state. This is again a guess that I'm saying. I think because this is how the population logic works. Chicago is again a populous place, and it's also the capital crime, right? It used to be very notorious back in 1930s. So I am also attaching one more library, factor extra. And what are we doing now is, even before we, and you can see the NB cluster, right? We have started using the NB cluster now. So what are we trying to do is, can we like find out the number of clusters, and we are using one more method. One method was that before even we do the clusters, can we find out the number of clusters? That would be okay. This method is some people call it the WSS method, but popularly this is known as the scree plot or the elbow plot, right? This is known as the elbow plot. Why is it known? I mean, if you look at a human elbow, then how does it look like? If you look at a so if I look at a elbow plot, then the elbow will look like this, isn't it? A human elbow is like this, right? So what does it mean? That we'll plot this. So we'll see this is the stable part of it, and this is my elbow, right? So this resembles an elbow plot. Some people call it the elbow plot. Some people call it the scree plot. You spell it like this, SCREE, scree, the scree plot, right? And also this is also known as the WSS method, whatever you may prefer to call it, right? So let's go ahead and then plot it, and then let's see what we get out of it. Okay, so I'm just executing this command, and on the right I'll have some. These packages have beautiful colors. I mean, they're and can you look at the plot quality? I mean, this is really good, right? So that's why these packages are good. The plot quality is really good. So what do you get here? Total within sum of squares. So the within sum of squares, I always, what do I want to do? I want to minimize the within sum of squares. Then only it is a good cluster, isn't it? If the within sum of square is 0, that means that's the ideal situation. So you can see this is like a elbow, and wherever the elbow, and this elbow is here, right? So I say this particular thing should have 4 clusters. So the WSS method is suggesting me 4 clusters. You can see this is the number of clusters that are being suggested. So this WSS method is actually proposing 4 number of clusters out here. Okay, now you can use a PAM if you want, right? So I'll set a seed. Why do we set a seed? We set a seed so that replicability, I've told you, we always set a seed so that if you are running the solution in cluster, it will not matter even if you don't set the seed. But there are techniques like classification and all those things where random things are generated. In those cases, it is important to set a seed. If you don't set a seed, then what will happen is if you run the cluster in your machine and I run it, you might see minor differences there, right? To avoid those minor differences or to ensure replicability, we use something known as set.seed. I've used 1, 2, 3. You can use 70, 80, anything. Some number is used which should be common between you and me. That is important. So I use some number and you also use the same number. That is important. The value of the number is not important, right? So I'm not setting the seed because you are not working on it. So what I do is I go for K means, right? K means I done a K medioid earlier, K medioid or PAM. PAM is a part of the cluster package and K means is a part of the base package. So I say, please do a K means for me because the WSS method told me there should be 4 clusters. So I go ahead and do this and I say print kem.res. So I'll say print this and this print, when I print this, it gives me this output, right? It gives me a good output. So it tells me like this thing. So can you see this? The cluster means automatically, it has done automatic profiling. So, and this profiling, don't forget, this profiling is done on the Z value thing. So if the value is negative, that means it is low on that attribute, which is good, right? And if the value is positive, that means it is above average, right? And average is bad, right? The average, so below average is a good situation and above average is a criminal kind of a situation, right? So look at this first cluster, it is negative on murders, least on murders, right? Least on assaults, least on burglary, least on rapes, right? So this is a bunch of very, very safe cities, right? Ideal cities. We should be living in that. Uh, there would be examples here, like what kind of cities are we talking? Like Iowa, Maine, Idaho, Kentucky. They are absolutely safe cities, right? Almost the safest one in everything. Okay, but I think the problem would be it will not have jobs. Otherwise, people will like to live in that, isn't it? So probably North Dakota, New Hampshire, Montana, very rare kind of cities. As Indians, we don't hear much about them. So probably this means there will not be much of jobs. If you want safety and want to enjoy life, these are good states there. This is the second group of cities where you see safe but less safer than the first group. You can see still this is the second lowest murders happen here. Assault is also second lowest. This burglary is at third place. So, I mean, people go looting. So there is personal safety. The asset safety is not very high, and women's safety is also okay, not a problem, right? So this is the second thing. And look at these guys. What are these? Highest on murders, the highest on assaults, right? And women's safety is better here and burglary is also not high. So the personal safety is not good if you look at it in these states. In these states, if you look at it, then the murder is the third highest, assaults are the highest. They are, I mean, the property is not at all safe out here, right? And not at all safe for women. So this should be the worst kind of states, right? So the group 3 should be the worst kind of states, right? And which are this is, so look at it immediately, like California props up, right? So California, Colorado is like since 1800s. I mean, we hear these places are have been very, very unsafe, right? Or New Mexico, right? All these are southwestern kind of states, right? Which had this cowboy and gun culture. Texas, all of them are there. So you can watch Clint Eastwood movies, right? Clint Eastwood, very nice hero. So his trilogy, Fistful of Dollars, A Few More Dollars, probably that very clearly depict this culture. Very nice movies. Okay. So this is there. So my knowledge comes from there actually. I haven't read newspapers, but that's the impression that I carry. So within cluster sum of squares by cluster, if you look at it, what it says is that if you look between SS and if you look at the total sum of squares explained, this is 71.2. Higher the better. So this shows that this is a very nice clustering solution. Anything above 60% is good. This is what it says. And this is the fourth cluster is actually a very cohesive kind. Oh, sorry, it's the sum of squares will reflect. If it is high, it reflects a very large cluster. If it is low, it will reflect a cohesive cluster. So the fourth cluster is actually a very cohesive cluster, right? This is not a very cohesive cluster. Should be a miscellaneous kind of a cluster. If I don't belong to cluster number 1, 2, 3, I'll get it here. Now, as you change your algorithm, the output also changes. If you ask me, is this kind of output available with every clustering algorithm? My answer is no, right? So total withinness, betweenness. So this is the advantage that you get when you are using the k-means. But the k-means, I said you, technically the problem is it uses it takes average. Now, what does the average of West Virginia and Wisconsin mean? Probably nothing. In PAM, what is going to happen is it's actually going to use the actual states as my centers. But the other problem would be that it will not give me this output. So there is a problem. There are different algorithms. At times you have to go through different algorithms and see what you want, what you don't want. But not everything is available with every algorithm, right? So I'm adding one more dimension of complication. So that's why this is a bit complicated. And always understand the more algorithms you know, and if you think your confusion is going to get cleared, it's not. Actually, you're going to get more confused, at least initially. When you keep on doing it many times, probably you will carve out a method and say, okay, this works for me, this doesn't work for me, isn't it? So that happens. Now we can calculate the now this entire thing, the averages were based on the z-scores. What I want is the actual means, the actual data. I want the means of the actual data. So aggregate is the command. I'm saying take the USRS data, list by what? The cluster KM, the cluster thing. So do it by cluster and find out the means on the actual values. So I run this and this is what I see. So the fourth cluster, you can see the murder rate is 13.93. This is 3 point, this is per 1000 people, right? So 13 point, or this is for the year. I don't know. I'm a bit confused, whatever it is, but this is a high, this thing. And you can see here, it's the assault. This is 257 as compared to 78. Huge difference. Burglary, this is 56, 52. Rapes 33, and this is 12, the highest one, right? So this is how you can make a profile of the states. That's what I'm saying. Now, if you want to put the cluster membership with in the arrest data itself, then I told you cbind is the command. Cbind means you are binding two data sets according to the column, right? So you are combining them, right? You are adding variables, right? Adding columns, cbind, bind by columns. And the condition is that whatever data sets you are binding, they should have equal number of rows. Otherwise, it will return an error. Okay. So what are we binding? It's a US arrest data, which is 4 variables. And this is cluster membership. It is 1 variable. So the final data set DD should have 5 columns, right? So I'll do this and let's check whether if this is the case. Yes, these are the 4 variables, and this is the membership that has come, right? So there's a 5th variable. So by looking at it, you can understand what is the situation. This is the 4th thing. Alabama belongs to the 4th, this thing. Alaska is an open place. I don't know why it is at the 3rd thing. I thought it should be a very nice place, right? But it is not actually. Alaska, right? There also, I mean, in the snow also, people commit crimes. So cluster number, if you want to see the cluster size, right? So clusters, I'm just quickly showing some of the things, right? So this is how the cluster membership is: 13 in the first cluster, 16 in the second, 30. So 13 and 8 out of the 50, that is 21 are highly unsafe if I look at it in one or the other aspect. And 13 and 16, 29 are safe states, right? This is what we conclude. And if I want to look at the centers, because this is a means based thing, so it are the centers here. K means will have centers, so these are the centers, right? That we have already seen. Now let's do a plot. This is the MDS plot that I'm showing you. This seems to be a bit complicated thing, but and if you are wondering what are these numbers, right? This stuff. So these are color numbers. These are part of ggplot2, and the number of colors that are available to me in R is 255. And these are some numbers which are given, right? I don't know what these mean, but probably you can have a list of this and vary this. So I'm just executing this command, and let's see what do we get. It will take some time. Okay, and then let me zoom it. And this is what I see. So this is the MDS plot in 2 dimensions. This is dimension 1, it accounts for 62% of the variations. And this is dimension 2, which accounts for 24.7% of the dimensions. So in combination, 62 and 24. How much is this? This is, we are looking at 86.7% of the information. So that's really very good. And it shows that my cluster solution is really good, right? Separated. Now you see a overlap here. Now think about it this way. What is an MDS? So let us spend some time in understanding what an MDS is. Look at the room in which you are sitting, right? And assume there are that in this entire 3D space, you have tennis balls which are hanging around, right? Different tennis balls which are hanging around. Now think of those tennis balls, that there would be a shadow of the tennis balls which would be lying on the floor, right? So this I'll call it as projection. I'll giving it a name. This is the projection. Or if I drop a perpendicular from this tennis ball or this point, the center of the tennis ball to the floor, I'll get some point marked on the floor. Now, after some time, just imagine that the floor, that whatever projections I have on the floor, I just carry that. So what have I done? I have crushed this data from 3 dimensions to 2 dimensions, and this is what MDS does. So this is like my floor. This is the length and this is the width of that floor, and these are the 2 dimensions. So otherwise this is a 4 dimension data. This actually, the clusters are 4 dimension balls. What have we done? We have crushed those dimensions into 2 dimensions. One more point. Think of 2 balls which are suspended one over the other. Now look at your room again, and let's say there is a ball which is at a height of 3 feet. There is another ball which is at a height of 4 feet and bang above this first ball. And if I take a projection of it, what will you see? You will see a overlap, clear overlap. But why this overlap? Why are we seeing an overlap in this? Because there is one dimension of information which is missing, which is the height thing. If I supply that dimension, then I clearly know that these clusters are actually not overlapping. They are far apart, right? But this overlap that I'm see, I don't know. This may be because of this situation, because they are overlapping. They are, let's say, common in 1 dimension, or is it that they are really intersecting? So I don't know they are intersecting, or this is just because 1 dimension is missing. That's why I'm seeing this. The example of the tennis ball that I've given you. Okay. So if I want to, let's say, find out further, this particular command may not, I think this does not give me a leverage to find that out, right? This is not possible. I don't know. I'll have to go back and check that if this allows me to plot it in dimension 1 and dimension 4. Probably there I might get a clue that they are separated, and there might be some and there is no clear overlap, or there is overlap, I don't know. But this is not serious. This is something very, very marginal, right? So it's a good solution. This is what it feels
So,
right now, right?
so these
Yeah.
dimension 1 and dimension 2 signify.
So, okay, we'll discuss that. Right now I'm holding it, but dimension 1 and dimension 2, what happens is when you have data, you can actually break it into 4 dimensions, and these dimensions are based on into a new coordinate system. This coordinate system is based on this idea that we should have an axis where the variation is maximum. Your data is variation, 100% variation. So I devise 4 new dimensions coordinates where axis 1 has the maximum, let's say, deviation that is covered, right? Maximum variation that is there. The second dimension would have a lesser variation. The third dimension still will have a lesser variation, and the fourth dimension would have the least variation. Now this approach is known as the eigenvalue approach, right? So when we can break our coordinates into something known as eigenvalues. I'll discuss that, but I'll do it when we discuss principal component analysis. That is the right time to discuss this, right? So for now, you can just understand that this dimension 1 means it is representing the maximum variation, right? And dimension 2, the second highest variation. So you can see a lot of difference, 62%, and the other is 24.7%. Both of them combined explain 86.7% of the variation in the data, which is a large variation. So whatever we are seeing is very, very reliable because we have covered how much variation? 86.7%, that is 87% of the variation. This is what it means, okay, right now. But when we do a PCA, probably you'll be able to appreciate it a bit more because we'll get into a bit more details there, right? I'll do it then instead of going into too many details here, okay? So you can do a PAM also on this. So let's see what does PAM say, because the WSS method said that we should have what? 4 clusters. So let's look at what PAM says if you go for a 4 cluster thing. So I'm going here and I say use the sellout method and please let me know what is the number of clusters. So I'm using the sellout thing this time and I'm asking for the number of clusters. Okay. So let's see what the, now look at this. Sellout says there should only be 2 clusters. So do you see a difference? The elbow method told me 4 clusters. The sellout thing says only 2 clusters. That's all. All right. And it also says it's very, very stringent, right? It says even if you go with that, your cluster quality is only going to be how much? 4.4 something, which is a very poor quality. And you can see any other place for a 4 cluster thing, look at the average sellout width. That's going to be absolutely less than 0.4, which is not acceptable. This is what the sellout thing says. So now what I am telling you is this is the confusion. So clustering, though it is a very easy thing, this is all kind of a soup that you land into. So what to use? So at times ignorance is also bliss. So when people don't know all this and they bravely go ahead and do a clustering thing, I mean, they are good also. For a person like me, it's a lot of confusion out there, right? Now this guy says there should be only 2 clusters. That's all. So, okay, I agree and say, let me go for a 2 cluster solution. So I go for a 2 cluster solution. I print this and what do I see? It gives me memberships and let me look at the medioids. So what I'll do is, so the representative states, I'll not do everything out here, right? Because otherwise it will take a lot of time. Okay, so I'll say that let me look at the medioids. So show me the medioids. So it says that New Mexico and Nebraska are the medioids. So it says there are only 2 groups, safe states and the non-safe states. The safe states are like Nebraska, right? And this is what they'll resemble. You can see their scores are low on everything. And this says that New Mexico is the represented. It's like notorious places, right? You can see a whole lot of things out there, right? So if I plot this, let's see what do I see. I'm doing MDS plot of this. So you can just zoom it right now. Then you can see this, right? So again, you see this overlap, but I have my doubt. This may be an actual overlap, or I don't know. This is because of dimension crushing. But you can see all these states are the ones which are notorious kind, and these are the safe ones, right? You see a whole lot of safe states. Oh, sorry. Okay, so this is what now. We'll also cover one more algorithm which is known as Clara, right? Clara is the algorithm that you use
But
when
then
you are
Amit I know something. So, uh, like you said, ignorance is bliss sometimes. If a person does not know many things, then he uses one approach which he knows, and then whatever clusters 2, 4, 5, 6 he gets is okay. But
okay.
if the confusion between 2 approaches, say 2 cluster or 4
Yeah.
clusters, then how do I know
Yeah.
which is better?
Okay, so I think what we can do is then it is probably, as I said, that question I'm just holding back for now, right? Okay, so I haven't given a definitive answer. So right now what we are doing is we are adding to the confusion, that's all, right? So the cluster right now you feel it, there is, at least all of you agree there is some confusion out there, okay? And the ignorance is bliss kind of a thing can get somebody killed also at times, okay? So may not be a very good idea. I mean, ignorance definitely is not good, at least in machine learning. Okay, so what we have done is we have added to a confusion dimension. That's all right. But so let's go ahead with the things and let's see if we can clarify this, right? Because first time we need to look at all the confusing dimensions, the dimensions which confuse us, and then we look at the solutions. So what I'm trying to say is there a single solution available? Probably not, right? Because there are multiple dimensions which are creating confusion. So there has to be multiple ways of removing those confusions. So right now we are sort of diverging, then we'll start converging. Okay, that's what we'll do. Okay, but in between, what I've come across, and this is something which is a different thing which has come in between, because this convergence is fine. And before I do the divergence of it, let me discuss one more algorithm, which is by the name of Clara, right? Sorry. So Clara, when do we use Clara? Clara we'll use when the data set is very, very large, right? Then we use Clara. Otherwise, what will happen? I told you, if you have million rows, then the system may not be in a position to handle the distance matrix. That will become very, very complicated, and it will take a lot of time. So Clara is nothing but a PAM that is used on a large cluster. So how is it done? It's commonsensical, as I said. Everything in clustering is commonsensical, right? So let's say this is a large data set that I have. Large means not in terms of variables, but in terms of rows, right? So let's say I have millions of rows out here, many millions. Let's say 10 million rows out here, right? So if I straight away run a PAM on it, you will not get any solution, believe me. You can just type it and the system will not, it will keep on working, and after a lot of time, it will tell you there is no solution, right? It hasn't converged, or it will not do anything, right? So what we do is we break this data set into multiple data sets. We can define how many data sets we want to break it, right? So we'll break it into, let's say, 100 data sets. We can do that, right? We can tell the system 1 to 100. We break it into how many data sets? 100 data sets, right? And remember, this is a very large data set. And how is this breaking happens? This 100 would we break it on a random basis, right? Not a subjective thing. So 10 million doesn't mean that the top this many I'll put in one cluster, then the second bunch I'll put in. No, not this way. This would be based on random sampling, right? Why do we do a random sampling? So that the properties, the entire properties of this big data set are, I mean, we maintain the properties. That is the idea. That's why we'll have this kind of a situation. Okay, so that why do we do random sampling? So that the properties of the original data set are sort of maintained. I'll not say if you divide anything, the properties are absolutely going to be maintained. That's a doubt, but if it is a very large data set, like example 10 million, then the chances of these properties being maintained across 100 data sets is a very fairly high chance. But if there are only 1000 rows and you divide it into 10 groups, then the chances are that the original data set and the subsets may vary in property, right? That can happen. But in large data set, there are chances, if I divided it into 100 groups, the properties may be maintained. If I provided I don't use my subjective selection. I don't say that select the top 100 and put it in data set 1 or something. These are equal numbers, right? So 10 million divided by 100. So every let's say group data set will have so many things. Okay, this is what I'm saying right now. So this is the number in which I divide. I can decide that, right? And then what will happen? Also, because this is a k-means, remember this is a k-means. That means k is fixed all across. So I'll tell all of you guys, divide your data into 5 clusters. So all of them will divide their data into 5 clusters. And ultimately, I'll combine the results cluster wise. So cluster 1 of every group will get together, cluster 2 of every group will get together, cluster 3 of every group will get together, and cluster 5 of every group will be put together. So this is a k-means for a very large data set. Remember that, okay? And this is how it works. So here what this is what we are doing. So let's run Clara. This is not an absolutely large data set. You can pick up some data set. There are large data sets available. You can practice on that. I'm not putting the seed, but it's a synthetic data set which is generated and available in R. So what I'm doing is we are having 2 rows of data only. So I'm generating R norm. Always understand when I say R, that means we are generating numbers from what distribution norm. If I put it R UNIF, RUNIF means generate data set from a uniform distribution. And this is RBIOM, then this means I'm generating data set from a binomial distribution. So R means generating data. So if I'm generating data from a normal distribution, then which normal distribution and how many data points I want? So 2000 data sets I want from a normal distribution which has a mean 0 and which has a standard deviation of 8. I want 2000 data sets from a normal distribution. So I want them separately, 2000 here, 2000 here from the same normal distribution. Then I have normal distribution, again 3000 data points I want. The average should be 50, the standard deviation should be 80. So you can see there is a huge difference between the means of these two normal distributions, right? And I combine them. C bind means combine them. So and also what I'm doing is I'm giving the columns names. So the name that I'm giving is X and Y. These are the names of the column or variable names. Also I'm giving row names DF. So paste 0 means what? It will create paste 0 and put S before everything. And the second portion should be what? The number of the rows. So let's look at this and let's see what is generated, right? So this should have 5000 entries. This is one. The column should be named as X and Y, and the row should be named as S1, S2, S3. This is what I want. Now I can just do ahead of this and you can see this. So this is X and Y, right? And you can see the row names S1, S2, S3. They'll be till 5000. If I do a tail, let's do a tail on this. So let's, a tail means the bottom 6, right? So if I do a tail on this, you'll come to know how many are there. Okay, so I'll say enter. So this is what I was saying. This is 5000 entries and there is XY here, right? So total 5000. So I'm treating this as a large data set, though this is not a large data set. So let's see how many, because I've generated the data set, I know there should be only 2 clusters because I've used only 2 normal distributions to generate it. So if I've used 2 normal distributions to generate this data, then it should only have 2 clusters. So I'm asking Sil out what is the number of clusters that I should use. So I use this thing and it will do a sell out thing on this. And what does it say? Let me have the result. So it says that should be 2 clusters, and look at this. Look at the cluster thing. 0.8, magnificent, because this is artificially created data. It's a perfect normal distribution data, right? And even by chance, if you choose something like at 3 clusters also, then also it is around 0.5, right? So I'm just showing you that's why I like this sell out thing, right? I can use a WSS also here, right? So let's see what does the WSS tell me. It should also tell me too, isn't it? Because so I'm just putting it here so that I don't have to type it out here. Let's say I'll put a hash mark and put it here for some time. And let's say I want to use a WSS method, WSS method. So let's see what does the WSS tell me. It will take some time, right? Because there's a large data set. Now, can you see WSS is taking time? So you have to wait. That is the reason I didn't put WSS straight away, because it takes time. We are waiting. So now you understand this is what happens. Now, if let's say these become 10,000, then what is going to happen? The WSS is almost going to die. So the WSS also, the elbow is here. So I'll say, okay, this also says 2 clusters, right? Because this is a very synthetic data set I said. So everything will converge. No confusions. The sellout and WSS are in agreement, right? So the moral of the story is that you may not get a confusion every time, right? If your data set is good, then they both may actually agree. That can also happen, okay? So what are we doing? Let's look at the algorithm, Clara. So we are using the Clara command, very easy. Just instead of PAM, Clara, I'll say DF, and I want 2 clusters because this is what sellout had advised. And I want 50 samples to be done. So the 550,000 data I want to divide into 50 samples. So each sample will have how much? You can just calculate 100 only, right? So 50 parallel things will happen. And I wanted PAM like, right? So this is PAM like is equal to true. So I'll just do it, run. And you can see it's over in a moment, right? because it's not a large data set, otherwise we would have been in trouble, right? So I'll say run, and this is what you see. Okay, so there are, like, I can combine this, I can do all that. So I can just combine this, and head you will see this, that the first 2500 would be cluster 1 and the last ones would be cluster 2. You can look at this, the last one, because this is how I made the data. It's a very open kind of a situation, very known situation, right? So this is here. So you can keep on looking at it. And what are the medioids? If I want to look at the medioids, so number 250, value number 250 and 2424 are the representatives of this, right? And if I want to look at the MDS plot, let's have a look at the MDS plot also. So it shows me very clean cluster. Can you see this? A huge difference out here. Okay, so nice, good. Now hierarchical clustering, so this I'll go very quickly because I've done the hierarchical clustering for you, because I've taken the bottom up approach. So generally, like when I discuss this, I start from the row 1 actually, right? So for you, I've taken a different approach. So hierarchical clustering, we know it, right? Let's not, I'm not going to invest too much of our time here. I'm just saying it. Compute the dissimilarity matrix, you know it now. I want to see it like a matrix, so that's fine. Now this time I'm doing a hclust. Just look at it. Hclust is the command. I'm using the distance matrix. You can use the distance matrix or you can use the original data. And method means the linkage. Remember that, right? What am I doing? Method means the linkage. Which linkage? So what's d2 is a linkage also, and it is a method also. So I'm using a what d2 as the linkage method. Okay. So what d2 is my linkage method. Average, so I discussed 4. This is the 5th one. What d2, what distance square, very popular one. So I've done that, right? I'm using a library which is mclust. Again, a heavy library. And now we'll do some, we'll start looking at some details, so that that confusion that initially was created, how do I understand whether that was a real confusion or artificial confusion, or how near or how far I am when I'm proposing these kind of solutions, right? So let's do this. And I see a dendrogram immediately. This is the dendrogram, right? When I look at the dendrogram, if I look at the jump kind of a thing, it's telling me 4 clusters because I'm moving my fingers out here. I'm putting a cut here, so I clearly see 4 cluster solution, right? So this happens to be a better solution. So it's telling me there should be 4 groups, right? So I have one more method which is telling me 4 clusters. So I've used 3 methods. Out of the 3, 2 are telling me 4 clusters, 1 is telling me 2 clusters. So understand rule of majority is also one very important thing. Now what I'm doing is we are computing something known as the Cope-Hentig distance. Now what is the Cope-Hentig distance? Let me open something for you. You can also open Google if you want, and just type, say, what is Cope-Hentig distance, right? What is Cope-Hentig distance? What is this? Have I typed the spelling wrong? Let me just check. Cope-Hentig, it is. Cope-Hentig distances. There is no E. So the spelling is wrong. That's why. This is the reason. Getting this. Yeah. So we have Cope-Hentig correlation, Cope-Hentig function. So Cope-Hentig, what is a Cope-Hentig coefficient? So somebody has put a tutorial also for your benefit, right? Cope-Hentig distance for hierarchical clustering. Let's look at it quickly and let's understand what it is, right? Why I'm doing this is we are trying to understand together. That's all. So at times, this is a very friendly, you get everything here if you want, right? So do we have something? It's first. So let's read here whatever we have. How good is the clustering that we just performed, right? This is an index called cross correlation coefficient or Cope-Hentig correlation coefficient, CP, that showed the goodness of fit of our clustering similar to correlation coefficient of regression. So what have we come to? Now this is the area where you'll not find very easily. If you look at clustering methods that are given on the web, Or one thing I guarantee you, go to any machine learning course, they don't discuss all this stuff. So whatever I'm discussing right now is not available in your mass online classes. You may go to any of the course that you want, any course on clustering, NUNGs or anybody's. They don't discuss all these things there. And when you actually work on the business thing, this is what saves you. That confusion I told you, that ignorance that I told you, this is the way to partially avoid that ignorance. So, so this is like a correlation thing between what? The distance matrix and the copyantic matrix. Now, what does this mean? Let me explain it to you. And this is a machine learning approach. Now, I'm coming to a generalized kind of machine learning approach, right? And which is not only applicable to clustering, it's applicable to other algorithms also, other methods also. So I'll mention one of the methods so that you have a proof that it really matters. So I'm discussing the approach. See, this is the distance matrix that we have. We start with the distance matrix, you know, right? And we take some steps, intermediate steps. And what do we get in the end? We get a dendrogram kind of a thing, right? We get a dendrogram kind of a thing. So if this process in between is actually good, then these two should be the same thing, isn't it? These should be the same thing. I don't know how many of you read this poem. They're very nice poem also that probably you can all read very, you should all read. I read a lot, that's why I tell you so many things. So let me just show you that poem also. So the name of the poem is Man with a Blue Guitar. With a blue guitar, right? See, all these things, the way like I'm telling you, at times what happens is we are when I go to take, let's say, classes for a PhD thing. At times I'm called for taking classes in for PhD students also. So when PhD students are taught, they are not taught the codes, right? That's a very bad method of training PhD students because they need to be thought leaders. That's why they are PhDs. So they need to need the philosophy also, the larger philosophy of things, not just like just executing codes here and there. That anybody can do. That's a ITI method. How do you make electrician look at the red wire? Please don't touch it because there would be a current in it. This is one method. And how are engineers trained? Probably they are told that there would be three phases. What is the difference between phases? So they have that uh, that capability to design things, right? So there's the philosophy of machine learning that I'm discussing. So you can just read this. So Stephen Wallace, and this is one of the poems that I always use. So you can see it is written, the man bent over his guitar, right? A shearman of sorts, the day was green. They said, you have a blue guitar. Generally, I've seen guitars are what? I mean, they're woody colors, they're wooden colors, isn't it? Now, this guy was roaming around with a blue guitar. And if you see somebody roaming around with a blue guitar, you'll find something odd about it, isn't it? And what did they say? You don't play things as they are. So you let's say this is applicable to the machine learning experts also. So you make a cluster solution which where actually there is no cluster actually, right? So you do not play things as they are, right? This is accusation generally. So the men replied, things as they are changed upon the blue guitar, right? So now I'm using a cluster solution and the actual thing actually got changed. So what kind of like cluster solution I'm giving? So am I the man with the blue guitar? Then they said, but you must play. So they are saying they are, so the men that is that somebody, the Stephen Wallace is talking about are your customers. And they are saying, but play you must attune beyond us, but yet ourselves, isn't it? So this is the requirement. So you have a blue guitar, that's fine. You are not one of us. Okay. You are a data scientist, machine learning expert, that's fine. But remember that you must play a tune beyond us, something which we cannot imagine. A clustering we can't do. It's a complicated thing. You must do that. But yet we should be sure that that's correct one and we should be able to understand it, isn't it? A tune upon the blue guitar of things exactly as they are, right? So do it that way. So he answered. Now this is what the amateur machine learning guy will always answer. I cannot bring a world quite around. I cannot. I mean that's true also. I cannot. You can see there's a lot of confusion here. So I can't bring the world quite around. I mean, but it cannot be that it's like completely changed. Although I patch it as I can. This is what I try my best. I sing a hero's head, large eye, bearded bronze, but not a man, isn't it? So in poetry, it's not a normal human being. You make him super normal or something like that, right? So this is a nice poem. You can read it. It's Stephen Wallace, The Man with the Blue Guitar, right? Also, like how we should, the approach of a how should you approach your methods in general when you have a large toolkit. So I don't know how many of you seen this serial which used to come, Bharat Ek Khoj. That was the serial, and which was based on Nehru's book Discovery of India, right? And this used to come when I was also very young, right? Around 7th 8th class, or something like that, right? Or 10th maximum, that's all. So this Bharat Ek Khoj, if you remember the words that used to come, so there was a slok that used to come from the Vedas, right? So that's a very nice this thing. So if you look at Indians thousands of years back, there were people who were not blind believers of God. We were skeptics, right? That's the word that we are saying. So somewhere we were skeptics. So being skeptic always pushes your knowledge boundaries, right? Though people may not look very positively towards you, but some part of you should be skeptic. That's very, very important. And if you look at the words, they loosely translate into that who knows what was there before this nature. People say it is somebody who made all this. So they are referring to God, right? And then he says, okay, that this guy is there whom we call as God, but what is he acting like? He's just sitting like a chairman somewhere above, not visible to anything. And we say he knew. So was there something known as truth and let's say false before the nature was formed? We doubt it. And even this person who's God, does he knew it? That's again a doubt, right? So we had been skeptical. So read those lines. They're in Sanskrit, but there's a English translation and the Hindi translations also available. It. So like, as I said, we as data scientists should be skeptical about things, always be skeptical about things, right? That can only help us. That can only help us beat ignorance, right? And that's one hypothesis that we always create, right? So is this the correct solution? Is actual the beta equal to 0? So we are acting like a skeptic there. That's why that hypothesis testing, right? If we are not skeptical, we'll say, oh, the machine, this algorithm has done a good job over, finished, right? Fine. So coming back to this idea, coming to this stuff. So now what I was discussing, the larger philosophy of it. So when I say, so if you believe in these two things, right? The man with the blue guitar, and if you think you are a skeptic, you'll always try and find out methods of ascertaining whether the model that I'm proposing is good or not. And there would be something available, believe me, if you search it. At times the search is hard and long, at times it is easy. So this is the distance matrix. Now coming back again to this philosophy. So this is a distance matrix, right? I do some few things in between. And what is that few thing? I do the clustering, and then it is transformed into a dendrogram, right? Which is also a translation of a correlation kind of a thing, a distance kind of a thing. So how faithful is this ultimate transformation? This is what I try to measure. I try to measure the correlation between this. Given this and this, if the correlation is high, that means the process in between was good. And if this correlation is bad, then this is like the man with the blue guitar. The things have changed after coming onto his guitar, right? A simple man has become a bronze statue, isn't it? That's what have happened. And there is very little resemblance, though they may resemble, but physically and functionally they are very, very different, right? So this is what we do. And if you ask me, is this kind of a thing used at other places also? Yes, it is used. We are not going to discuss this technique, but again, as I said, very heavily used in marketing analytics, which is known as structure equation modeling, SEM, or some people call it by the name of path analysis. Generally used for knowing the key drivers. So some people might come to you and say, I make lot of sales and I do not know what are the reasons why my product sells vis-a-vis as a competitor sells. So that's known as key driver analysis. Why is some product selling the way it is selling? What are the things which are driving the sale? So that's known as the, so from an application perspective, for business people, it is known as the key driver analysis. For the machine learning guys, and these are out and out statistical techniques. There is no machine learning out here, right? Purely statistical techniques. So that's why I'm not included here, because they are purely statistical technique. Anything which is statistical, I am not included here. So structure equation modeling or path analysis, right? So there also what happens is you start with a covariance matrix or a correlation matrix, right? So you start with a covariance matrix there, and then something happens the way like you are running a clustering solution here, we run a path solution there, we break it into paths, and finally we again get a covariance matrix which is derived out of this. So we look at how do these covariance metrics actually compare? Are they similar or not? So for comparing covariance metrics, you cannot use a correlation matrix. That's a bad idea. So we use a chi-square. We use a chi-square to compare whether this is this, right? So this I am giving you two examples where you start with a particular form, you do something in between, and you try to reconstruct that particular matrix again from your solution. And if these two match, then this is a good solution. So here we start with the distance matrix. You have a dendrogram. From a dendrogram, we reconstruct the distance matrix. If both of them are in unison, then this is a good solution. Otherwise, this is bad. This is known as copacentic distance. Copacentic distance means the correlation between the original distance matrix and the one reconstructed from the dendrogram. Right now, we can go and read this page. Probably should make a little bit more sense to you. So you can see this, right? So the distance matrix and the copacentic matrix is constructed from the dendrogram, right? So this is the original distance matrix and this is the copacentic thing, right? So this is how it is constructed. I'm not getting into the details of it, right? So how it is constructed now, the next question could be that. So you can keep on asking question and it will keep on diverging, but right now I'm just saying that let me look at the copacentic matrix. I'm constructing the copacentic matrix right now. And this is a copacentic matrix. This is how it will look like. So there was the original distance matrix and this is the copacentic matrix. Now what will I do? I'll see a correlation between the original distance matrix and the copacentic matrix. This is what I'm doing. Now let me have a look at it. So I'll say run. So 70% of it is the actual thing, 30% is a variation. So I'll say anything which is greater than 60% is a strong correlation. So I'll say it's a good solution. Whatever solution I run, that was a good solution. Now, okay. Now let's do one more thing. If you look at this method, what I had done is I had used the WORDS method here, right? What method I'd used? The WORD method. Now let me change my linkage method. Okay, so now this time I'm going to change my method. I'm going to put it average. Instead of a WORD D2, I'm going to use the average method for clustering, right? And I'm going for how many cluster solution did I go here? Here, like in this case, I had gone for a H cluster and I had gone for some the cluster solution. I didn't bother about the cluster solution too much. Okay, but what I'm doing here is I'm finding a correlation this time again with the original distance matrix and with the copacentic of the second one, which is the average method. Let's see what is the correlation I get. So do you look at it? I get a higher this thing. So it means, so I have a guiding thing. Now do you see the divergence is starting to clear? So the copacentic distance tells me that instead of using what D2 as a linkage method, use average as the linkage method. That is better, right? So I have some guidance here. Similarly, I can vary my distance metrics. I can vary my clustering algorithms and keep on looking at copacentic distances, and that can give me a guide which is probably a better one, right? So there are multiple ways of doing it, and whatever, and you do multiple things, of course not everything will converge, but whatever the majority says is a better thing, propose that as a cluster method. That's the way of getting into the way of doing it, right? So copacentic distance is also available. All these things are available. Okay, so now so we have done a clustering and we have done 4 clusters, right? So you can, this is a colorful dendrogram, that's all. It shows 4 colors, the 4 groups. You can see this, the first cluster is here, the second cluster is here, the third cluster is here. 4 colors it is used, so you can very clearly see how the states fall, right, in 4 clusters. So this is a dendrogram, a colorful dendrogram if you want, right? That's all. So these are the commands which are for that. And if you want to see MDS plot of this, then this is the MDS plot. Of course, you'll see MDS plot as earlier, right? But this time instead of like spheres, you will see this octagon because I've opted for this kind of a thing. So you can see octagonal kind of a thing here, or this irregular thing, kind of a thing, right? So you can go for a space that you want, right? What kind of figures you want. Okay, so all this is there. That ignis command, just to show you how the ignis command can be used. So this will require your cluster package X. You can straight away use the data matrix, right? Right now we are not using the distance matrix. So should we standardize it? True, right? It will automatically standardize. So we are giving the raw data. Can you see this raw data? We are telling the system, please standardize it. Metric means what method to use. We are saying Euclidean. What is the linkage method we should use? Please use what method. That's known as method, right? So this is ignis. Straight away you can do ignis out here. I'm just showing you the commands, right? Diana is divisive, as I said, divisive analysis clustering. That's why it is known as Diana. X, again the same thing, standardization correct metric equal to Euclid. And the only difference is this is Diana here, that was ignis there. That's all. So how you run it, right? So if you want to look at the dendrogram for the ignis thing, you can look at it this way. So this is how it looks like. You want to look it for this, so let me just zoom it. So this is how it looks like for four. It proposes 4 clusters, and this is what we have. And k equal to 4. See this if you want 4 clusters, then what should the dendrogram look like? And here also, what would the dendrogram look like? It was returning an error, yes, last time. I don't know. It shows not returning an error. Right, it returns some error actually. I don't know. So I need to check. I haven't checked it. Let's try it. Yeah, it returns an error. There is some problem out there. Okay, so let me see if it works for 3. There's some error. I need to go back and check this, right? Why it is returning an error. So let me put it this way. Last time also it is returning. I forgot to check it. Now, can we compare two dendrograms? Right. So one I did a coparentic distance. That's fine. Coparentic distance mean what about the original distance matrix versus this one? Right. So I think we have exceeded time. My 10 minutes I did not like come to know about it. So what we'll do is we'll stop here for today, and the next time we'll in the next session we'll compare. There very little. I mean there are few important things which are left. So we'll finish that off. That's one thing we'll do, and then we'll start with a new topic, which is again very popular, too much in use. We'll start with classification. Classification is one of the most important machine learning techniques, right? So we'll start with clustering. We'll start with classification. We'll finish this idea of clustering, and then we'll go ahead and do start the classification thing, right?